Okay, there's a lot of algebra in this one. So I pre-made kind of the worksheet, but this is me doing the derivation of an elastic collision. First of all collisions, whether they're elastic, inelastic, or completely inelastic, conserve momentum. Collisions and explosions conserve momentum because there's no external force. If there's no external force, there's no changing the system's momentum, which means the momentum before and the momentum afterwards are the same. However, if a collision is truly elastic, then we also conserve energy. And so what I've done is I've looked at this special case, which is the most popular case, in which we have M1 moving at V0 hitting M2. And if you're told that the collision is elastic, then you can say that yes, we conserve momentum, of course we do, and we conserve energy. So in this particular example, these all work. Now again, these equations are only true for this particular situation if it's elastic. If it's not elastic, these aren't true. If it's M2 is also moving, then there are new equations that we'd have to derive. But this is a pretty popular scenario that I want to kind of walk you through. So the original momentum, which I call P1, is only M1 V0. The momentum afterwards is M1 V1 plus M2 V2. We don't know what's happening. Maybe M1 hits and rebounds, maybe it hits and goes through. It doesn't really matter. Maybe it hits and stops. But we are just predicting that M1 will have its own velocity afterwards and M2 will have its own velocity afterwards. So this conserves momentum. From an energy standpoint, we're only talking about kinetic, and the original kinetic energy is just 1/2 M1 V0 squared, and the final kinetic energy is 1/2 M1 V1 squared plus 1/2 M2 V2 squared. They both have their own velocities and their own kinetic energies afterwards, but it must have got converted from the original energy. And again, these statements are only both true if it's elastic. The rest of this is me just doing algebra, solving for V1 and V2 in terms of the given quantities. So the three given quantities are the two masses and the original velocity of M1. If you give me those three things, you should be able to predict V1 and V2 after the collision. Okay, and now I'm just going to kind of talk you through the algebra that leads me to these results. So over here, I took the momentum equation and I solved V1 in terms of everything else. It didn't happen to be V1, I could have done V2, but I just picked V1 using momentum, and I took that V1 and I substituted it in for V1 into the energy equation. I did get rid of those halves algebraically just to simplify it a little bit. So I plug this value into V1 and get this line. Then I multiplied all of that out, taking the M1 squared over here. I did notice that this term has an M1 over an M1 squared, so I canceled the M1 and canceled the squared. I also, with this M1 that's left in the denominator, I multiplied everything by M1, which got rid of the denominator. I put another M1 over here, got rid of the M1 on this guy, and put another M1 on this term. Okay, then I have this line. Once I get here, I realize those two are actually identical, which means I can subtract both and I can get a 0. Then I have this line. All of them have, all the terms have a V2, so I can divide everything by V2. Divide by V2, get rid of the V2 squared and just leave a V2, get rid of the squared. Then here, I realize that everything had an M2, get rid of one of the powers of M2 and get rid of M2, and I'm left with this. I did factor out a V2 from both of those terms and I'm left with one of the M2s and one of the M1s, and then I divided. And I can show then that V2, the velocity of box 2 after the elastic collision, is 2m1 over m1 plus m2 times v0, right? It's some fraction of the original velocity. From a dimensional analysis, this has to be, what it is. This is some unitless number, which is just a ratio, times a velocity to then produce a velocity. I then took this result for V2 and plugged it in for V2 right here. So I went back to the original line attempting to solve for V1. So I took this and I put it into V2, which is this line here. I then distributed, I multiplied everything by M1 plus M2 to get rid of the denominators. I canceled M1s. I rearranged the terms a little bit. So this is 1 m2 v naught, and this is 2 m, sorry, this is 1 m2 v naught, and this is 2 m2 v naught. So I subtract that over to get a minus m2 v naught. Then I factor the v1 and divide it, and it looks similar, except v1 is equal to m1 minus m2 over m1 plus m2 times v naught. Again, it's some fraction of v naught. And now I have the equations for v2 and v1 based on knowing this original condition and the fact that it's elastic. Again, if you change this or you change this, then these equations are no longer true, and you have to do a whole nother set of algebra to kind of like derive what the elastic equations look like. I do think some of these make sense when you look at the limits. So you could look at the limit of what happens if m1 is equal to m2. Well, that really ends up being like our shuffleboard example. If m1 equals m2 and we chuck m1 and hit an equal mass m2, we have, or we will talk about in class, the fact that m1 will stop and m2 will go on, again, assuming that's elastic. And if you look at the equations, we look at that limiting case, if m1 equals m2, we get a v1 of 0, which makes sense. Again, it's like a shuffleboard puck hitting another shuffleboard puck. If you hit it head on, it'll completely stop and the other one will fly off. And not only will it fly off, but if m1 equals m2, this is 2m1 over, well, if these two are equal, it's really just another 2m1, so v2 equals v naught. Check. If our equations make sense based on that restriction. What happens if m1 is way less than m2, as if m2 was a wall? Well, if you chuck something into a wall and it's elastic, and this is really massive, then m1 will actually bounce off that way with negative v naught, and m2 will have 0 velocity. And so if you plug those in here, that will also make sense. If m1 is much less than m2, then this is really just a 0, and this is a 0, and this is this ratio has been negative 1. So v1 equals negative v naught, exactly what we said. If m1 is much, 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 much less than m2, m1 will have v1 of negative v naught. Looking over here, if m1 is much, much less, then this is infinitely bigger than those. Then this is basically just some finite number divided by infinity, and so v2 is equal to 0. Yes, if you throw a bouncy ball against a wall, that's what this is saying, bouncy ball versus wall, the bouncy ball will bounce off with negative v naught, and the wall won't have any velocity. The harder one is to determine, and again, it's a little more difficult, what happens if m1 is much, much bigger than m2? If m1 is much, much bigger than m2, we do predict that v1 should be v naught, because basically if a truck hits a bouncy ball, the truck's going to still be going at v naught, and that is true. If you make m1 bigger than, much, much bigger than m2, those don't do anything, and you get m1 over m1, which is just 1 v naught, so v1 equals v naught, which makes sense. And it will turn out that v2, if m1 is really, really big, m2 doesn't matter, and you get v2 is 2 v naught. And that's something you probably couldn't have predicted, but you do now know as a fact that if you have an elastic collision and something really big hits something really small, the small thing will bounce forward at twice the original velocity. Again, you can look at this sheet. I think I posted a PDF of it. You should be able to handle all the algebra steps. There's no calculus. It's just a lot of foiling and canceling and subtracting and a little factoring at the end. This is the derivation of the two elastic collision equations that we will use in class, as well as the discussion. And I know I talked kind of fast, and we can do more of this in class if you want, but looking at those predictive limits that we know what happens in these three like big cases, and the equations make sense based on those situations.